Let me add it. Okay. All right. So I think it should be fine now, right?
Yes.
Cool. Yeah. So today I'm gonna talk about two papers about high resolution cascaded diffusion model, image gen and image gen video. They are works released by Google. And yeah, so before I start, I want to first do some review about the important points about diffusion model we have talked about. So as a reminder, diffusion models are latent variable models that obey a forward process. That obey a forward process QZX starting at data X that follows the distribution of PX. So it's kind of just like keeps adding the Gaussian noise step by step until the final distribution just follows a normal distribution. So that's the forward process of the diffusion model. And the diffusion model is actually trying to learn to reverse the forward process, and the goal is it can be reduced to learning to denoise this noised input into an estimated X hat data approximately equal to the original input. So the loss function can be seen here. So X will be the original input and ZT is the noised version. Lambda T is kind of like the power of the noise, and C is conditioning vectors signal, and you just try to reconstruct the input image from these inputs. So that's the learning goal of the diffusion model. Yeah, these are already things we talked about in the previous weeks. And so once we train a diffusion model with the noise goal, when we want to generate the image, we need to sampling from a trained model, and it can be performed in several ways. The most straightforward way is called discrete time ancestral sampling. So it basically follows the first note that the forward process can be described in reverse as this. So given the t, where t is actually larger than s, then the s follows this normal distribution. We just need to predict this mu, and then we can sampling from this distribution to get a more clear version of the image. So, and the process can be written in this way. So ZT will be the input noise, will be the noise input, and X height theta is the prediction output by the diffusion model, and epsilon is noise we sample, standard Gaussian noise we sample from. So and we do this sampling step by step. That's how we can sample from the diffusion model. There actually later work show that the denoising model can be used to deterministically map noise to a sample X by numerically solving the probability flow ODE like this. So following this idea, if the update rule specified by this sampler is written in this way. And yeah, I'm not sure if this sampler has talked about in previous week, but yeah, probably I think Fred briefly mentioned about ODE thing.
I don't think this one was covered in detail.
Okay, so maybe I will talk a little more about the idea of this one. So yeah, I didn't look at the mathematical details, so I couldn't derive the mathematics behind it today, but the idea is so it proposed that sampling can be done by numeratically solving this probability flow ODE, this one. And this ODE can actually, so P theta is defined here, and F and G are defined here. And since X theta is parameterized by a neural network, this equation is actually a special case of a neural ODE. And you can solve it by some traditional integration rule, integration solver, ODE solver. But they propose this DDM sampler, and it can be understood as an integration rule for this ODE. But even though it was originally proposed with different motivation, and this is the DDIM rule for the update. So I think the important thing is you need is that this DDIM sampler provides a deterministic mapping from a noise Z to a sample X. So it's a one-to-one mapping. So that's what's the difference between this DDIM sampler from this previous discrete time ancestral sampling. So that's the difference of this part. And actually today's work, imaging video relies more on this DDM sampler.
I just want to have a comment to this DDM sample. I think what they did is they originally the sampling, because this is originally they used the SDE to the reverse SDE to the reverse process. But then the reverse SDE there to sample from the SDE, they encounter a lot of scalability issues. So this one is much faster, but it's the result it obtains it as it's less versatile compared to the previous one. Yeah, because the noise time is down.
Yeah. Thanks for the comments. Yeah, so that's the sampling for diffusion model. And Shuchang last week talked about conditional diffusion model. And so the motivation for the conditional diffusion model is kind of like, assume this is the probability X given the condition in C learned by the model. When we do sampling with, so that we want to sample from this one instead of this one. So the difference is that we emphasize more on the mode of the distribution, which means so you can think this mode, the data points here have higher quality. So you want to increase, you want to sample more data points from this mode of the distribution. So you by changing the distribution from this one to this one, you decrease the diversity of the samples, but increase the quality of each individual sample. So that's one of the motivation behind the conditional diffusion model. And to do that, there are like classifier guidance, classifier guidance and classifier free guidance. And today's two works relies more on this classifier free guidance, which is the last two row here. Yeah, and yeah, the first one is, yeah, so the second one, you have a trained classifier, and you use this classifier to as a guidance to help you focus more on the, so you can see that there is a probability y given xt, so you move your step towards the ones that increase the probability of this image have a label of y. And this one is actually similar to this one, except you just replace the classifier with an inner product between two embeddings, but it's basically the same idea. Yeah, but today we actually will focus more on the classifier free guidance. So epsilon is kind of like the step you take to do the sampling. You can, and when this is empty set, it means you don't have any conditioning samples. And when it has Y or C, it means you have these conditioning samples. So what this means is you can think of when you have this one minus this one. So you kind of have like two steps, two directions. This direction focuses more on the condition, the ones with the conditioning tokens, and this one without. So by minus them, you actually focus more on the direction that's unique to the conditioning caption C. So when you add this step, you can actually shift the distribution from this one to this one. Or like another way of thinking it is kind of like if you think theta is kind of like a distribution. So one of the theta, this one, can we think of distribution of like this, and this one is the distribution like this. And when you use this distribution minus this distribution, you actually the results is more like it will be things more like this one. So you emphasize the parts that's unique to this label Y or caption C. So that's the equation behind this classifier-free guidance.
What is the empty set in the condition? Does that mean you don't condition on anything?
Yeah, that's correct. Yeah, you need a label, but you don't need a classifier model. Yeah, this one is a classifier model. Yeah, this one will be like act as a classifier. So it is kind of like a model to evaluate the consistency between this embedding and the caption. Yeah. Yeah.
Yeah, so in this case, it's not that complicated, but they made it able to complete. So they call it Clipper because they don't see Clipper as a classifier. So Clipper is a model for you to get an embeddings for image and text. You can turn it into a zero-shot classifier. But they distinguish the Y and the C because they treat C as a caption sentence, but the Y just as a label. So they are saying in this case, you have this caption sentence. You just use the text encoder inside the clip to get it embedded. And then use the image encoder inside to get an image and do the dot product of this. So in other words, for the classifier guidance, we may have say maybe logistic model guidance. You see that you get any kind of classifier you can have. Just for click is one single model.
Yeah, so that's why it's not. Itself is not selected.
Yeah, so because they don't think of the classifier.
That's why the third one is for the classified free guidance. We can talk to the table free guidance. That's why we need this guidance.
But in all cases, there's some supervision going on, right?
I think in this case we can put 2 and 3 into one category, saying that you need to depend on a separate model, whether it's classified or classified model. So it's just the last one. Maybe it's more like model, other models. You don't depend on any other model, just your own model.
Yeah. Okay, so that's the conditional diffusion model. So a summary. Diffusion models are a class of generative models that convert Gaussian noise into samples from a learned data distribution via an iterative denoising process. And ancestral sampling and DDIM are two common ways to sample from diffusion model. And DDIM can deterministically maps Gaussian noise to samples. A classifier and classifier get free guidance plus a way to trade off the diversity and fidelity of samples. Okay, so now let's officially move on to the imaging and imaging review. So first, we can see here are some samples about the pictures generated by imaging. And I think you can see that it actually have a very good quality and also very high resolution. And also this one, actually pretty cool. And here's an overview of the models of the imaging. So this one is actually not an end-to-end model. It consists of, say, four different models. So the first one is a text encoder, which given a text, just transfer them into embeddings. And then this image generator converts Gaussian noise conditioning on this text encoding and output a 64 × 64 low resolution image. And then this super resolution model try to improve the resolution of this picture. So the input will be like 64 × 64 image, and it will generate a more clear 256 × 256 resolution images. And this one also conditioning on the text embedding. And then another super resolution model is applied to generate the final high resolution images. So it has 4 models, and it can be divided into 3 kinds: the text encoder, the image generator, and super resolution model. And let's first look at the text encoder. So the text encoder in imaging is the encoder network of T5, which is text-to-text transferring transformer. It's a language model released by Google in 2019. And by the way, the encoder is totally frozen during training, so it doesn't update parameters in it. So T5 is a text-to-text model that serves as a general framework for many NLP texts by framing them as text-to-text problems like language translation. So the input will be translated English to German, that is good, and the output is just translation. Or like code a sentence, the course is jumping well, and it's just output is not acceptable, which means this sentence is not acceptable. And this one is kind of like, I think it's the rhino gets on the grass, a rhino is getting in a field, is measure the similarity between 2 sentences. It outputs a score of 3.8. And this one summarizes a sentence in upright summarization. So it's a language model supports all kinds of tasks. And the question we probably want to ask is why T5? So previous work used text encoder trained on the paired image to text data, like clip. And it's actually a standard way in previous text image models because they may encode visually semantic and meaningful representations. However, extremely large language models, by virtue of their sheer size alone, may still learn meaningful representations. And in this work, they actually find that scaling the text encoder size matters. And well, the encoder they use and clip is the model trained on this image text data, performs similarly on simple benchmarks. Human evaluators actually prefer this large language model on drawer bench, which is a more challenging benchmark raised in this paper. So that's the text encoder. And for the diffusion neural network architecture, so both image generator and super resolution model, which is this one, and this one. So all of them are actually diffusion models. And the difference is that image generators only conditions text encoding will the super resolution models conditioning on both text encoding and the low resolution images. And the only restriction for the architecture of the neural network is that the input and output eventually must be the same size, And the authors decided to use the UNet architecture as the basis of the neural network. They proposed some modification over UNet to make it more efficient, but we'll skip this modification because they are just more detailed, they are just engineering details. And here's a picture of the architecture of UNet. So the green one is the input, and the green one here is the output. It's kind of like if you're familiar with the convolutional neural networks, it just this part is kind of like the most of the convolutional network. It's just shrink in, you just increase the inception field and increase the channel, and when it becomes the highest resolution, then you just upsampling it to the back to the origin, the side of the input images. And it also adds some skip connection between the input and output of the same resolution to keep improving performance. So that's the architecture of the UNet. And here there's a residual block. And the residual block looks like this. It is a batch normalization plus ReLU plus convolutional network. So that's the architecture of the UNet. And maybe people will ask how to condition the text encoding and the resolution of the images. So one way to do that is just add them into the images. So that's one way to do that. And another way you can also use like cross-attention transformer. So that's not a standard way, but there's a lot of ways to do the to add the conditioning encoding into the input model. And then we will talk about the classifier-free guidance. So previously we talk about we can use classifier guidance to improve sample quality while reducing diversity. So specifically, it jointly trains a single diffusion model on conditional and unconditional objectives by randomly dropping C during training. And then the sampling is performed using the adjust X prediction like this, which we have already seen it before. It's the same as the previous slides. And here, W is the guidance weight. You see that setting at W1 disables classifier free because you don't have the second term, you only have first term, which is the most straightforward sampling. We're increasing W larger than 1, strengthening the effect of guidance, which is this part. And imagine depends critically on classifier-free guidance for effective text conditioning. And you can see the effect of the classifier-free guidance. So when you like the input prompt is a religious place, if you use unguided, it outputs all kinds of religious places. But some of them actually, like this one, has little to do with the religious place. But if you increase the guidance weight, you can see all of them are images of churches. They are kind of like, so less diverse, but the quality improves. So that's the effect of classifier-free guidance. However, they noticed that although classifier-free guidance is a powerful way to improve the caption alignment of generated images, but it has been previously observed that extremely high guidance weights damage fidelity by yielding saturated and unnatural images. So like the picture shown on the right. So this 1, 2, 3, 4, 5 is the guidance weight. And you can see that when you increase the guidance weights, the background turns into black. So the background just disappears. And when the guidance weight is extremely large, the whole picture, the whole images just become a black image. So that's a problem. And the authors investigate this phenomenon and find that it arises from a train test mismatch. In particular, the pixel values for the training data are scaled to the range of -1 to 1, but high guidance weights cause the network outputs to exceed these bounds at a given time step. And to make matters worse, since the model is iteratively applied to its own output during diffusion, this effect compounds as the diffusion process and proceeds. This process proceeds, leading even potentially to divergence. However, high guidance weights are found to be crucial for achieving state-of-the-art image quality, so avoiding the problem by simply using lower guidance weights is not an option. So to solve this issue, the most straightforward solution is to simply clip the pixel values at each time stamp to -1 to 1. And they call this approach static thresholding. So this method was in fact used, but not emphasized in previous work. However, this technique still results in oversaturated and less detailed images as the guidance width further increases. So in this work, they propose another technique called dynamic thresholding. So at each time step, a certain percentile absolute pixel value is chosen. And if that percentile value exceeds 1, then the pixel values are thresholded to -s and s, and then divided by s. So what does this mean? We actually have a series of figures to illustrate this. So like this is the distribution of all the pixel values. And if they choose the 80th percentile pixel value, and if this percentile's value is smaller or equal to 1, then actually there's no dynamic scaling. They just keep the output image the same as the input of the next step. But if this percentile value is larger than 1, then they will do the dynamically scale. So in this case, the percentile value is equals to 1.35. It's larger than 1, so they will do this dynamic thresholding. So first, they collapse all pixel values beyond the negative or positive this threshold to the threshold itself. So in this case, we have threshold will be 1.35. So all the pixels whose absolute value is larger than 1.35 is just threshold to 1.35. So it will become like this. And then you divide all pixel values by the values of the 18th percentile pixel, so which is 1.35, to scale all the pixel values back to -1 and 1. So the resulting distribution will look like this. So that's the basically visualization of dynamic thresholding. So you can see that the distribution has a gravitational pullback towards 0, affecting all pixels and not just the saturated ones. So according to this block, it comments this threshold that it has the effect of bringing all pixel values back to the range of -1 and 1, but operating on all pixels and not just those at the extremes. There's a gravitational pullback to 0, which balances the potential for divergence under an iteratively applied model. And in my understanding, for static thresholding, so it is possible that a large portion of the pixel values are thresholded to -1 and 1 when the variance is large. So, and that will result in a large portion of the picture become black. But for dynamic thresholding, it guarantees only a certain percentile of pixel values are thresholded to -1 and 1, while others pixel values are linearly scaled, so it is less likely to be oversaturated. And here's a comparison of the different thresholding technique. So you can see that when there's no thresholding, the whole image turns black. And for static thresholding, when the guidance weight is large, even though the front is fine, but background just becomes totally black. But when they use dynamic thresholding, the whole images are good, even though the guidance weight is large. So that's the effect of this dynamic thresholding. Well, Yeah, that's the novelty bring by this paper, but this paper is actually a combination of all kinds of techniques, but this technique, all those techniques are actually already published a paper, and they just composite them all together. This one is actually, I think, it's first proposed in this paper.
And the outcomes of models that I think the main idea is still coming from this conditioning. Conditioning model is the backbone.
Yeah, that's the backbone to train one diffusion model. But so actually, I'm gonna talk. So they have, remember in this overview picture, which is here. So each one is so this three, each one is a diffusion model, and the backbone to train one diffusion model is, as you said, is the classifier-free guidance. And then they also have some techniques to train, specifically designed to train this super resolution model. It is also a diffusion model, and yeah, so the input and output of like this super resolution model is both 256 times 256. This input is actually a conditioning tokens like this text encoding. So they just conditioning on this one and this one. So that's the difference between, yeah. Yeah, so yeah, I think it's just higher resolution and higher fidelity.
So if we compare with value or any other model using the FID method or using other methods?
Yeah,
So they have a quantitative.
yeah. So I don't think theoretical wise they provide any novelties. They just use all kinds of techniques like this standard thresholding. That's kind of important thing in the training, and they boost the performance of those all the matrix.
Because like I mentioned at the beginning of my time, so OpenAI and Google cannot do my computer. So today, these tools are both from Google Brain. Last time, those five were from Technique. I think one thing Google Brain is doing now is definitely was thinking about sales, that they can actually generate leads for the advertising. Yeah, that's it. For this one, it's probably just arguing that they can use the OpenAI model in terms of
Yeah. Yeah, this paper are just full of details.
Yeah.
Yeah, another thing is this noise conditioning augmentation. So they use this technique in the super resolution model in order to make them aware of the amount of noise added. So they just add another conditioning thing, which is the noise, how much is the amount of noise added. So this conditioning, they find it improves the sample quality and ability of the model to handle artifacts resulting from the lower resolution models. And they find it's very critical for generating high fidelity images. So the idea is like when you do the training, when you have this low resolutional images, and you have this high resolutional images. So what you do is you randomly sample aug level, which is the level of noise you want to add to the lower resolution model. So you apply this level of noise to these lower resolution images. And then you just do the diffusion model like in the normal way. So you just add an augmentation of noise perturbation to the lower resolution model. So that's they do during training. And when you do sampling, you also so when you do sampling, you will sweep over all the different values of the alg level to find the best quality. So you just iterate through all possible values of the alg level, and you apply to the alg level to this lower resolution images, and you generate the high resolution image in the normal way, and then I guess they just choose the one with the best quality. So that's this noise conditioning augmentation. Is also not too much normal. It's just a small technique used. So, and then that's all of the techniques in this paper. And for experiments,
Very confusing to me is that so this basically you do add some noise before you do the diffusion, right?
yeah,
But you also inject noise in diffusion. So why do you why does this help basically?
yeah. So this one, the diffusion is not, the noise is not added to the input. Remember, the input is the high resolution X. This XHR. The XLR is actually the conditioning thing, like the text tokens. So it's kind of like the C in the classifier free cadence. So normally it is you won't add this noise to that. They find adding this noise augmentation to this conditioning thing helps. Yeah. So in the experiments, so here are how many parameters contained in this model. So this 64 times 64 text-to-image models contains 2 billion parameters. And the first super resolution models contains 600 million parameters. And the third one contains 400 million parameters. And they find overfitting is not an issue during training. And they use Adam optimizer. And I will only improve the major experiments of this paper. So many observation studies to show the importance of each component skipped. So here is the results on Coho. It's a easier data set. So you can see that they compare with the DALI 2, the glide, using the zero-shot fidelity, and they achieve the best score. And they also do like a human evaluation to comparing model outputs and original image. So it's like a human evaluation of the quality. And an interesting thing is that so the original, when you do all the kinds of images, the score is like 40%. But if you exclude all the prompts containing the people, like man, woman, men, so you don't generate people images of about people, the score actually improves. So you think that this model is actually bad at generating images of people, but good at generating images of others. And here is a human evaluation about on this newer benchmark they released, what they call draw bench. So this one, each one they just compare their outputs with another model, and let human choose which one they prefer. And you can see that user preference rates is higher for imaging over all the baseline models. Yeah, so that's the imaging.
So the human to choose.
Yeah.
Are those human from deep mind?
No, I don't think they will do that. Because they are Google, so I guess they are rich. They can employ a lot of people to do the evaluation. Yeah. And then now we'll move on to the second paper, which is the imaging video, which actually can generate the video, a short video, given a text. Like when you have a small handcrafted wooden boat taking off to space, can generate a video like this. A person riding a bank, back in a sunset, kind of like this. Also, so actually, if you look at the images, you think it's pretty good, but actually, if you try to look at the real image video, it's actually not that good. For like I'm just open one thing. So these are all kinds of real videos they generate. And especially like this one, the kite one, you can see that the motion is still kind of weird, and or the horse. So I guess if you pick some frame, it's fine, but when you try to concatenate them together, it just still has some weird issue here.
So for this thing, it's like the January and the series of, right?
Yeah. Yeah. Yeah, but still, it's still quite impressive. So I'm back to my slides. Yeah, this is still the idea like of the diffusion model. So actually, I'm gonna talk. No, so actually you can see the overview of the model here. So same as the imaging, given the text prompt, it outputs this using the same text encoder T5XX large. It generates the encoding, and then this base model converts the conditioning on the text tokens and outputs 60 times 40 times 24 and 3 frames per second short video. So it will be a very short one, so it only have a few frames and very low resolution. And the idea is like using this TSR. So the TSR is called temporal super resolution. So this one specifically increase the number of frames in this video, but they don't increase the resolution of the videos. So you use one to generate the video of more frames, and then this one. Actually, I don't think they explicitly consider that. Yeah, so I think they just try to reconstruct the data points, the real video. They just try to learn that using the language model, but they don't have any techniques try to explicitly make sure this similarity thing happens.
So then for
No, it's just one sequence of one sentence. Yeah, but yeah, that would be too hard. They just have one sentence describing the contents summarization of the whole video.
So this is like for the base model, we only run 3 frames. Then we try to do interpolation between these frames to generate the intermediate.
Actually, it generates 16 frames. So the first number is the number of frames, and the last number is the size of the images. So the first one outputs 16 frames, and each second contains three frames. So it's like just 5 seconds of this low resolution video. And then this second, maybe I can use a laser point. And then this second TSR, temporal super resolution model, they increase the number of frames in this video. So it increased to 32 frames, and each second will contain 6 frames. But the resolution of the image is the same. And then the next two spatial super resolution model, they keep, so they don't change the number of frames. They just increase the resolution of each frame. So at this point, they will generate a 320 times 192 resolution images frames, and in total they only have 32 frames. And then they keep increasing the number of frames. They will get 128 frames, well 24 frames per second. So actually, if you know about cartoon, you know that 24 frames per second is basically the ones you, for human eyes, can distinguish that. And then the last spatial resolution model keeps increasing the resolution of the video.
So for the base model, we already have 16 images.
Yeah. And then, so they use 3D UNet for the as the basis of each diffusion model. So first, we already seen the 2D UNet. The 3D UNet is very likely, very similar. So each block represents a 4D tensor, with axis labeled as frame times height times width times channel, persists as in a space-time factorized manner as described. So we'll show that later. So it's similar to the video. You just shrinking the size to downsampling, and when the downsampling to a certain size, then you upsampling to restore the original size as the output. And here is I think the most important space-time separate block. So for each frame, they have this spatial con and spatial attention, which just operated on single frame. And then they have this temporal attention or temporal convolution that mix all the frames temporal information together and then outputs the video with temporal resolution. So you can see that spatial operations are performed independently over frames with shared parameters. Yeah, so each of these frames are models with shared parameters, whereas the temporal operations mix these activations over frames. So our base model uses spatial convolutions, spatial self-attentions, and temporal self-attentions. For memory efficiency, our spatial and temporal super resolution models use temporal convolutions instead of attentions. Our models at highest spatial resolution do not have spatial attention. So this block, each block is kind of the arrow here, how they change this one to this one. They use this space-time separate block. And they use a lot of same techniques as in imaging, like the classifier for guidance, the noise conditioning augmentation, and the dynamic thresholding. And by the way, in this paper, they find that dynamic thresholding is not enough to avoid the problem of oversaturating. So they therefore use this oscillating guidance. They use a constant high guidance weight for the initial sample steps, and then oscillate between a high and a low guidance weight at each alternating sampling step, and which they find significantly helpful. So they emphasize that a constant high guidance weight at the start of sampling helps break modes with heavy emphasis text. Where oscillating between high and low guidance weights helps maintain a strong text alignment. This is done via high guidance sampling step, and we're limiting saturating artifacts via low guidance sampling step. And then another technique they used to help the training is use video image joint training. So the video text data is actually not enough. It's small and less diverse. So they want to utilize the image text data sets during training. And they do that by treating images as single frame videos.
by packing the images into a sequence of the same length as a video, and they bypass all the temporal blocks. So this strategy increased the overall quality of video samples and allows knowledge transfer from images to videos. So for example, the models can learn different image styles that's not contained in the video. So like this one. So a cat eating food of bowl instead of Van Gogh. So we know there are no videos in the style of Van Gogh, because they add the images of Van Gogh painting, so they can learn the style of Van Gogh. And also, watercolor printing can also be done, and the pixel art can also be done. So this image video demonstrates the ability of the model to generate dynamics in different artistic styles. So that's thanks to the video image training.
So this sequence of, let's say, the cat, and so we created all of these images and put them back.
Oh, this are the output of diffusion model.
Mhm.
So this like in the video and image joint training. So the video data sets doesn't contain anything about Van Gogh.
Mhm.
The images, the image text data sets, they contain a lot of images of Van Gogh's painting,
Mhm.
right? So in this, and by training the video and image together, the model learns what's the style of Van Gogh. So they can create the video of the style of Van Gogh.
I think you just mentioned the image as like a single frame video.
Yeah, here is a straight images as single frame videos.
So if you packing images into a sequence, and how can I make sure when I pack images together, it will look like a video?
No, it's kind of like just the same images, copy,
Like this is the
paste.
same image.
Yeah.
Okay.
So when you look at it, it's just an image. You can see that it actually bypass all the temporal blocks.
Okay, but when we generate it, we can generate like a sequence of the same lines, but with images slightly different from each other. So it can, otherwise it will be like a.
No, so like during training,
Mhm.
the image, if the input data are images, then the training process basically the same as the image in.
Mhm.
So your output is still an image, not a video.
Okay.
So in this way, it's like, so because they bypass all the temporal blocks, but the spatial blocks, they learn what's the style of Van Gogh.
Okay. 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 I see.
And then even though they only train on spatial blocks, they can still, the whole model can generate the videos in the style of Van Gogh or other paintings. That's actually kind of interesting. And another technique used in this paper is progressive dissolution. So recall that for a specific guidance weight, you can use DDIM sampler to deterministically map the Gaussian noise to samples. And the update step of DDIM is given here. So it's a deterministic step. And also here, you don't have the classifier guidance weights. But when the classifier guidance weight is adopted, then this X theta ZT should be replaced by this one. But a downside of DDM sampler is that to obtain a high quality sample, it needs to take hundreds or thousands of update steps, which is quite slow, especially if you're generating a video. So therefore, actually in an earlier paper, but also Thayer's paper, they propose a technique called progressive dissolution to distill a DDM sampler, a diffusion model that takes many fewer steps to generate the images. And this approach can be decomposed into 2 steps. So in step 1, given a range of guidance strengths they are interested in, they learn a model x eta1 with learnable parameters eta1 with the following objective. So basically, it tries to predict the output of this DDIM sampler with this W as the input of the model. So that's the first step. And in the second step, they progressively distill the model learned in the first step into a fewer step model, X hat eta2 with learnable parameters eta2 by halving the number of sampling steps each time. So basically, they train the student model to match the output of two-step DDIM sampling of the teacher. And then this step is repeated until the number of sampling steps is small enough. So here's a pseudocode for this step 2. So given the teacher model X eta, you do 2 steps. And you use this 2 steps to, so you do 2 steps. This will be the teacher X hat get it target. And then you use the student model to directly predict the output of the 2-step results. So in this way, the number of sampling steps needed is shrink by half, and then I keep doing that until the number of steps is small enough. So that's the idea of progress dissolution. But another thing about this progress dissolution is that, so we know that previous work choose to parameterize the noisy model to directly predicting epsilon instead of predicting the X hat. So in this case, X hat can be stored by epsilon using this formula. So, and the training loss is defined as here. So you just predict the noise with the input zeta Z. However, notice that at the initial sampling steps, when the t is close to 1, and when the alpha t is close to 0, you have this term 1 over alpha t, which is actually very unstable because alpha t is close to 0. So it is not a problem when we do hundreds of sampling steps, since the effect of early missteps is limited by clipping of Z, and later updates can correct these mistakes. However, when we try to decrease the number of sampling steps, then each step matters, then this alpha t becomes very unstable, and that's become a huge problem. So for this solution to work, we need to parameterize the diffusion model in a way for which the implied prediction X height remains stable no matter the value of alpha t and sigma t. So they choose to predict this V, which is defined here, and which gives X hat equals to this result. And you can see this is much more stable because they don't have a term like this. And the proof of this whole thing can be found in this paper, the progressive dissolution for fast sampling of diffusion models. So that's all the technique used in this image and video paper. So in the experiments, they train model on a combination of an internal data set consisting of 14 million video text pairs and 16 million image text pairs, and a public data set which contains 400 million image text data sets. And their image and video demonstrate some unique capabilities, like what we have already talked about. They can demonstrate the ability of the model to generate dynamics in different artistic styles. And second one is that so you can see this one are a 3D model rotating, and the shape of these objects basically makes sense. So it demonstrates the model's understanding of 3D structures. And the third one is they're all generating steps of generating a variety of text with different styles and dynamics. So these are all very interesting and unique abilities of this diffusion model compared to the earlier video generation model done by GAN or VAE.
So I remember from last time, I showed some like failure cases or how to generate a sign with word referring something. and then the model down to actually fail to do that. But in this case, even asking generated video afterwards, diffusion or image and video, seems like the model can do it.
Yeah, the model can do it.
Um,
So I guess it learns like what each alpha, each letter looks like.
Yeah, so one difference I noticed is that in the Darwin paper, when they did the talk, they didn't put the text they want in position. Here they put it in. I'm just guessing whether that whether the model has learned that when you see position marking in a prompt, you treat it as a text rather than something you need to understand. But I feel like being able to distinguish something as its abstract meaning versus something as a text you should show on the image is a really challenging task.
Yeah, yeah, but as I said, I think this quotation marks helps here. This comma, I think it helps. I'm not sure if we remove that, it still works. Okay, and so in experience, perhaps I think. Actually, I don't think so. They didn't provide the code or the API because some ethical issue. Actually, I'm not sure about that.
For DALI 1, we can start it. For DALI 2, we need to submit the application and then wait for the approval.
Yeah, so they find that, so in previous imaging paper, they find that scaling the parameters in the text encoder is more helpful than scaling the parameters in this UNet. But in this paper, they actually find that the parameters, scaling the parameter counts in the video UNet actually help. And they think it's because the generating video is a more difficult task. A UNet is the architecture of each diffusion model. So here, yeah, so each diffusion model, this one is just input video, and this one is the output video. That's the video UNet. And each arrow is a block like this. So you give a input video, you just as a UNet. So each this like this base model or TSR or SSR, each one of them is a video UNet. Yeah, because each one of them is a neural network, right? And these neural networks, they just given a noise, they try to denoise that. That's the usage of this neural network. And this neural network is actually the UNet, they use the architecture of this video UNet. So like this yellow one is the noise input, and it passed all kinds of components. And this one is the denoised version, denoised video. I don't understand. I mean, because this UNet, it can be a diffusion model, right? Because the input and output are actually the same dimensionality. Yeah.
So
Yeah, so yeah, let me maybe go through this overview again.
thick. So each block here is a diffusion model. And this one, so once you have this prompt, you use this language model to make them language text encoding. And like this diffusion model is conditioning on this text encoding, and it converts Gaussian noise into a low resolution video.
And the diffusion model has much to
Yeah.
and more. So it's there.
So this diffusion model, whole model is this UNet. So this UNet is a neural network. Yeah, it is the same. Yeah, so the internal ones are just the
Because sound from noise each time you generate a new. So we saw in the Gaussian sense, it's just like you change the Gaussian mean and you sample that, or like you sample noise icon and sample. So how do you get that noise? It's like using so imagine you originally have like, let's say 62 by 64 noise, 62 by 64 of noise. Then you want to go through multiple steps. Each time add another 62 by 62 sensor on top of that. And that one is then you do like this.
Yeah, so that's why I'm like, is it for just for one step?
yeah.
It's clear, right? So it's always this model. It's always this model. So yeah, it's like you have a 62 by 62 put into this model, goes through some middle step and give you another 50.
Yeah, so like during sampling, you apply this same model like several times to convert one noise into a video or image. No, no.
Otherwise, it's going to be ending.
Right, yeah. When you within this one, it's just the one diffusion model, it's one.
Yeah. So. Yeah, so again, I'm talking about defining a scaling the parameters counting UNet helps. And they also like compare the prediction parameterization. So like this is the input frames, and this is the epsilon prediction and V prediction. And they think the V prediction is generates images with higher quality, because you can see that they are suffering from unnatural global color shifts across frames. So the weight consistent is more consistent. Yeah, so that's basically all about the image and video model. And I was talking about they didn't release their code or any API because they worry that the video and image generative models may be misused for generated fake, hateful, explicit, or harmful content. And they actually find that the social biases and stereotypes in training data could impact the model activity, and actually their trained model already have some tendency of the stereotypes and biases, like they always, when they generate people, they tend to generate people with light skin. And also, so this both concerns these decisions of not releasing the code or the data or the API. Yeah, so yeah, that's all for today's, and these are all the reference. So actually, I think it's 5 papers, and they just use those techniques we mentioned in these 5 papers to get these 2 videos or to get these 2 projects.
Do you know this is the only paper doing the like for or image, actual image that are multiple different.
Yeah, that's probably the only one because they didn't compare with any baselines and it's already a paper in 2022. So I don't think there are other. Oh, yeah, see, they have this FVD score. So I think it's an extension of the FID score. I think it is done by per frame wise.
So
Yeah.
I guess that's, I don't know how you define FID, but I think about it is actually like, because for FID, we rely on the image map. So because you want to compare distributions, right? Some of the image you generate, you need to have a large pool of images to provide you a distribution to compare. In this case, you probably need to.
Actually, I think machine wise is kind of difficult because video and images they're for humans. So I think that's why they in the imaging paper they actually do a lot of human evaluation to demonstrate their model is better.
Although if you do things like FID, like you need to be able to include the one whole video to find representation. So I'm not sure for reps much information. Using two vectors saying videos are similar, but less of valuable.
Yeah, maybe I can check how do they compute the FVD. Yeah, so they have this. So they measure with several metrics such as FAD for individual frames and FAD. So FAD is actually for temporal consistency and frame-wise consistency. So this one is actually put occurs here. I'm not sure how it's computed.
So things like FAD is not like compared. Whether they're similar or not, but
Not.
for frames inside the 3D.
Yeah, they are comparing the.
Right.
Yeah. And other thing they are just doing frame-wise FAD and clip scores.
The still surprising to me if they don't do any explicit setting to enforce the consistency, just at the end they can also this either a video is consistency or generated video is low. That's like
Yeah,
we naturally probably need to do some work to make it happen.
yeah.
And yeah, I always suspect that because they only give you so few samples to take a look at, there may be a lot of failure cases they can show. And the images there look very similar, so maybe just some very slight distribution shift, and then there's really no like logic for those kind of high level logical consistency.
Yeah, and Zunil provides some unofficial pattern reclamation of imaging. Yeah, thanks for. Yeah. Actually, I don't think it actually do a good job on frame-wise consistency because if you see the motion of the animals, they're still weird. Lots of things, yes, the leg could disappear, could go away. Yeah, but still, that's quite interesting.
It's not outside either.
Yeah.
That's cool.
Because if you look at the background, you see like, other than the central outline, other things in the background seems also pretty stable.
Yeah, the background is pretty.
You know, they move a little bit, but it's like pretty stable. But like the teddy bear when you see the cars, it's not like one car suddenly disappearing.
Yeah, okay.
Okay.
Yes, I will stop the recording.